It's time to begin. The first thing here, I want to make sure everybody got my message. Oh, look, video quality went to nothing. Got my message that the homework tonight is due at 8 p.m. The Friday night homeworks, now I'm only looking at the calendar here in Nebraska. Sundown's probably earlier down there in Texas. But it will be between 5 and 10 minutes before sundown, just so I don't have students trying to finish up the homework after the Sabbath begins. So I want to make sure everybody's aware of when the homework's due. Also, let me go to the course webpage for a moment here, just to point out some things. A student was asking about the tracking of homework. Moodle has assignment completion tracking. You don't have to do this. It's just so you can feel at ease about things. But some of them you have to check off, and some of them are checked off automatically. Ones that have that solid border, you check it off. So, if you read chapter 1, you can say, oh, I did chapter 1 and check it off. If you've completed homework 1, you can check off, I completed homework 1, and so on. Other things like the labs will automatically be checked when you've submitted an assignment. So you can actually look at that and say, was it done? And you might ask, why the two different ways? And the reason is actually pretty simple. I only have the option of making it when a score is submitted, when something is uploaded, or when you check it. And so since your score is on Expert TA, it's not going to show up here when you do it on Expert TA. Got a question, Mr. Meckel?
Yeah, when I clicked on some of the concept coach and the homework assignments, it said, even though I completed on that website, it said it was overdue and hadn't been turned in. Is that a problem?
No, that's not. So yeah, and with the concept coaches, the scores on the concept coach won't show up for a while, because what I'm going to do is at the time of the first test, every day I am downloading who has submitted 5 minutes before class. And then at the time of test, I will check again the scores, and you will get 50 times the percent of problems that you submitted before it was due, plus 50 times the final score you had on that section at the time of the test. So that gives you, 50% is effort points, just doing it on time, and 50% is the score you got eventually. Got a question, Maranatha?
The concept coach, is it based, the credit, is it based on completion or correctness?
It's 50% on completion on time and 50% on correctness at the time of the test.
The students could hear that at Southwestern.
They could not?
They can't hear her talking, so they don't.
Oh, okay. Sorry. My student asked if the grades on Concept Coach were based on correctness of answers or just on the effort. And my answer was that 50% is on getting it done on time and 50% is on the correctness of the answers. Any questions there, Southwest? Okay, other things that I think I mentioned but people may not have paid attention to. These 4 things here that are highlighted are places where you can look at material. I'll get to it in a sec. Look at material that we have done in class. The first 3 are YouTube playlists where you can look at videos from whichever class thing you're in. And then the bottom 2 are just folders on Google Drive that will give you access to the slides that I'm using in class. If you go there before class, you'll see the slides as they are before class. After class, I'll save it, and then you will see them with the annotations. Okay, Paris had a question.
Yeah, on Concept Coach, makes you type in an answer and then select an answer. Mm-hmm. Is the correctness of your answer based on both of those, or just the one?
It's a good question. Okay, Paris asked what your grade on Concept Coach is actually based on, because you actually answer twice. Once you write a free form answer, and once you click an answer. The reason you have the 2 things is based on educational research that shows that people learn better when they first try to explain what they understand, and then they have some kind of confirmation. So the first one is something to help you learn better. The grade is actually based on what you check.
So if you write something wrong and then you put the right answer, you're still getting that.
That's right. So conceivably, a lazy student somebody who's really confident that they know the answers could just put A for the filling out the form part and then collect the right answer and get full credit.
Okay.
But the goal here is for people to actually think about and type in an answer to help them learn, right? Everything we do is to help you learn. It's not necessarily for grade. Okay, was that you had a question, Jordan? Same one? Okay. Yeah, Colton.
I actually have a question on fees. Like, I
The
can't quite
clickers.
figure out how to register for this class with it. I've got my
Um,
turning account registered. I just don't know how to.
If it's registered, then everything's fine as long as you go to channel 33.
Okay.
You only have to be registered one time.
I don't know if I had to register for the class.
No, you just have to be registered with Moodle once. Okay, any other questions before we get started? Question over here, Isaac? No? All right, then I shall go ahead and get to the lecture. So today we're going to add acceleration to the things we've learned about motion. So we learned in class on Wednesday, yes, I say Wednesday because I'm that kind of person, about speed, and we learned a little bit about velocity and adding vectors. And so I actually put the equations above the red line there are the calculus forms. They give you instantaneous. The instantaneous velocity is dx dt. That lowercase d also means change in, just like the capital delta means change in. The only difference is that lowercase d means that it's an infinitesimal, that's on the order of 1 over infinity sized change. So now, for the majority of you, you're not doing calculus. We're not going to be doing anything with that equation, but it actually can make sense to you even if you don't know calculus, as long as you know that d means just a really tiny change, whereas delta means a measurable change. So we had the two forms on the left of the blue line, the instantaneous speed and the average speed. How would I change these from speed into vector? Okay, I need to have the direction to make it the vector, the velocity. And how do I indicate that with the equations? Okay, I put an arrow above it. So if I were to put arrows like this, it's now saying that the average velocity is the change in displacement, well, the displacement actually, because displacement is change, divided by the change in time. So that symbol makes a difference. Now, in textbooks, they often, instead of using the arrow, they use a bold font. But of course, as I'm writing, I can't differentiate. This one's supposed to be bold, everybody knows. That's why we have the arrow over the top. Okay, acceleration is a rate again. Remember, speed was the rate of change in motion. Acceleration is the rate of change in speed. And actually, if I'm going to be accurate, I have to use the word velocity. Because changing direction is a change in velocity, changing speed is a change in velocity, and both of those are accelerations. So, you think about driving a car. When you accelerate the car, and I want to get an answer from somebody here at Southwestern. When you're driving the car, if you are going to accelerate, what does that mean to you?
Increase speed.
Okay, increase speed. And how do you make that happen? Okay, so you press on the gas pedal, you increase speed. That's what we think about. But that's not the only accelerator in the car, because anything that makes you change speed or change direction is technically an accelerator. So how else can we accelerate the car besides pressing on the gas pedal?
Turning the steering wheel.
Yeah, turning the steering wheel or pressing on the brake. Both of those will also cause accelerations. So when we talk about acceleration, we have to be aware it's not just speeding up. If you press on the brake, your velocity is in the forward direction. And what direction is your change in velocity, your acceleration? Opposite direction. So your acceleration does not have to be the same direction as your velocity. If you're changing direction, your velocity is forward and your acceleration is at 90 degrees to your velocity. So oftentimes people just assume that velocity, acceleration are virtually the same thing in the same direction. We're getting feedback from their mic system back to me. But the fact is that acceleration is rather independent of velocity, but the acceleration causes the velocity to change because it's measuring the rate. So let's get to looking at our first clicker question. This is our last day where your responses won't count. Remember, the clicker session ID is capital W, lowercase EBB, capital P, capital H, capital Y, capital S. It doesn't count today. It'll count when we come back to school on Monday. Okay, good. We have people with both smartphones and clickers who've responded. That's a good sign. Oh, and for people here in the classroom, in case you forgot, it's channel 33. It's all working today, Debbie.
Richard just texted me and he said that your presentation was covering up your notes. These things down here.
Thank you.
Yeah.
Okay, I'll give it about another 5 seconds and go on. Since it doesn't count toward your rate, it's not hurting anybody that I don't get them counted. Okay. Oh, and I should have mentioned before that this question tells you to answer all the ones that are correct, and so you have to put in multiple answers and then hit enter. And so the answers we got were 28, 3, 24, and 4. Now that's a pretty clear selection there. We had a large group that said the final position minus initial position is a correct statement for delta x. We had 24 that said the change in position is a correct statement. 4 said the position, and 3 said the initial position minus the final position. As one would hope, the vast majority.
We're trying to figure out
Trying
what
to
the
figure out why
problem
we
is
had the
the
feedback.
sound. Do we need to?
Well, it's going from me to them, and then we're getting feedback from them back. Because that's
So does Southwestern need to turn there?
Yeah, it's on their side. So the majority is correct here. Delta means change in or final minus initial. So change in or final minus initial. So both of those were correct answers. Okay, now a little interlude. When I was looking at the homework assignments, the problems to assign for due today, I noticed that I didn't talk about converting units. And units, as we talked about in lab, are very important. But sometimes people use weird units, like when you run a marathon, everybody says 26.2 miles. I can drive that. Running it, not so much. So how many kilometers is 26.2 miles? A very simple question. And wow, somebody who actually knows the answer. I wouldn't have known that. But that's, of course, because Okay, so how we do this, we'll start with just our number, 26.2 miles. And I'm going to use MI as my abbreviation for mile. And then we need to multiply by conversion factors. And conversion factors always have to have a value of unity, which is just a fancy word for 1. So I put here equivalences. 1 mile is 5,280 feet. So if I want to remove the miles and convert it to feet, I can just take this and multiply it by a ratio that has miles on bottom, so it will cancel with the miles on top, and feet on top. So I look at this equation, 1 mile is equal to 5,280 feet. If I want to make a ratio with feet on top and miles on bottom that's equal to 1, I will just divide both sides by 1 mile. Now the left side of that equation is 1, unity. The right side of the equation, 5,280 feet divided by 1 mile, so there's my conversion factor. Then my next one is, everybody knows, 12 inches in a foot. So what should I have for my, well, what unit-wise, what unit should be on the top for this next conversion factor to change it to inches? Okay, I should have inches on top. How do you determine that? Because I need the feet to cancel out, so I need the feet on bottom so they cancel on top. So I can have inches on top, feet on bottom. Just looking at this equivalence, I know that's going to be 12 inches over 1 foot. But I don't have to go through and do that division every time. I pretty much got that under control. Now the conversion, it's an exact conversion. 1 inch is exactly 2.54 centimeters. So I'm going to put inches on bottom, and I'll go ahead and put it in meters on top. So that's 0.0254. Great, no one's going to read that. Not because they don't want to necessarily, but because it's unreadable. And so if I multiply all those through, can somebody multiply them through? I certainly am not going to.
42 kilometers.
It's
in 6 days.
okay. Just give me a string of numbers. It's what?
42.16 order 8 kilometers. 42.2.
Okay, just taking all these numbers together, 42,164.8 meters.
42 kilometers.
Yes, meters.
Yeah, you can put it in meters now.
Okay.
Okay, now, with this number, notice I kept all of the digits that I could. How many significant digits do I actually have?
No, I keep all specific, but these are all infinitesimal, aren't they? Or
What do you guys say over there in Southwestern? I have 3 and 2 that I'm hearing in my classroom. Okay, the answer to this helps us to understand significant digits a little better. You got a question?
well, this is like 1 mile exactly 5,280
Yeah.
feet, and 1 foot exactly 12 inches. So don't they lose the significant figures? And probably.
All of the conversion factors I gave you were exact. Now, you may not have known that. If they weren't exact, like if 1 foot wasn't exactly 12 inches, I'd be down to 2 significant digits there. But because it's exact, that means it's infinite significant digits. Now, our textbook, obviously we don't have a front cover, so you don't have a physical textbook. Although if you go to the textbook website, you can see that you can buy them for $48.50 on Amazon, or I think you'll be able to get them cheaper at the bookstore. I tried to call yesterday, didn't get the bookstore manager, so I sent an email to Terry Lair. I'm not sure what the price that she'll get, but last year it was just a little under $40 if you want a physical textbook. But there is an appendix with conversion factors. Or you can always go to the National Institute of Standards, and it's whatever, their website to find the most exact known. Most conversions we don't know exactly, but you have like 10 digits in them. Well, if you only have 3 significant digits in your other numbers, you're probably good to just use 5. But make sure you don't have your conversion factors limit your significant digits. So the correct answer here was 3 because I started with 3 digits in my 26.2 miles. That's not exact. In fact, the lengths of marathons vary somewhat is what I've been led to believe. So that's how many meters. We have 3 significant digits, and I want it in kilometers. As a final step, how do I go from meters to kilometers? Divide by 1,000. So that's just divide by 1,000, move decimal over 3 places. 42.2 kilometers when I round it to 3 significant digits. Okay, so conversions, most everyone probably has done this already, but you can't just assume that everyone has the knowledge, so that's why we do it. Any questions on the conversion process? Moving on. Okay, a little practice for calculating average speed versus average velocity and then looking at graphs. This, of course, comes from the textbook. You can look at it in the textbook, whatever. But we have a person that takes a trip to the store that's 3 kilometers away. And they just drive to the store and they drive back. They don't stop at the store because why would you want to stop there? You just want to drive there. Okay, this is something like Your friend went shopping, you went to pick them up and bring them back home. Or for lazy people like me, my wife went shopping and I went to pick her up and bring her back home. She's a wonderful woman. So on the trip over, if it was 30 minutes, now let's just convert 30 minutes into hours and do our calculations in kilometers per hour. So on the trip over, the change in position, what was the change in position on the trip over? 3 kilometers. What's the time in hours for the trip over? It's a quarter of an hour because the entire round trip is a half hour. So for part 1, going to store, the average is equal to that distance, 3 kilometers, divided by the time, which was 1/4 of an hour, 15 minutes, 1/4 of an hour. Everybody here is pretty sharp at math and knows that 3 times 4 is? So we have 12 kilometers per hour is the average speed going to the store. Coming back, what's the average speed going to be? Right, that's as close to rhetorical as you can get. It's the same numbers, so it's got to be the same answer. So it's going to be 12 kilometers per hour coming back. Now, I really hope I didn't make any mistakes here. I can't imagine I did, but I don't know what the textbook has. They might say it's a half hour each way. If that's the case, then I'm off by factor 2 from the textbook. So I have the average speed going each way is 12 kilometers per hour. What's the average velocity for going to the store? What did you say, Hannah? Okay, so Hannah said positive. If it's a one-dimensional problem, I'm perfectly fine with that. You would need, if it's not a test problem, you need to define what direction is your positive direction. But the positive would indicate one direction. So as long as we say this direction is positive, then for the trip to the store, the average velocity was 12 kilometers per hour in the positive direction. And in the return trip, what's different? It's in the negative direction. What about the average velocity for the entire trip? 0. How do you come up with 0? The total displacement is 0. And so the total displacement divided by the total time for the entire trip is 0. What's the average speed for the entire trip? It's going to be still 12 kilometers per hour because you're going 12 kilometers per hour and then 12 kilometers per hour. Now, I'm not going to work this out. Just throw out this question that's always kind of silly. Suppose that you are driving from Lincoln to Omaha, and that's 60 miles, and you allocate 1 hour to get there. That's you're going to drive 60 miles in 1 hour for an average speed of 60 miles an hour. So you head off toward Omaha, and there's traffic on I-80. And so you find that when you get halfway there, you've traveled 30 miles, and you've already spent your allotted hour. How fast do you have to drive? So what is your average speed for that first half if you spend an hour to go 30 minutes? Or 30 miles. If I could remember the difference in miles and minutes, it'd make this work better. Okay, so you went 30 miles per hour because you did 30 miles in an hour. How fast do you have to go for the second half to get back to your average time of 60 miles per hour? You'd have to go infinite. Now, a lot of people, just looking at the problem, tend to think, okay, well, you did 30 miles an hour for the first half. If you do 90 miles an hour for the second half, 30 plus 90 is 120. You divide that by 2, and it's 60. But that's not the way it works. You're not just finding the average between the speeds. It's weighted by the time you spent at that speed. And so the easiest way is to just say, what's the total distance? What's the total time? And since you already spent your entire hour, you'd have to get to Omaha in 0 additional time to average 60 miles an hour, which of course is not possible. Here are graphs. Oh, good. I did have the time the same as the textbook. Here are graphs to illustrate the motion. graphs are extremely useful in physics. I guess I should stay here in the picture. Graphs are extremely useful in physics because you can look at the graph and you can get an instant picture of what's going on. You can understand. This first graph is position versus time. And so if I look at that graph, the first line has an upward slope and it's straight. So I look at that and I say, okay, as time increases, the distance is increasing in a linear fashion. Get to the halfway point, and now it has a downward slope. As time increases from the halfway point, the distance is decreasing. And so if we wanted to calculate the speed, remember the speed is change in position divided by change in time. Now, if I look at this graph, I'm just going to jump right to it. If you find the slope of the graph, what is the slope of the graph? What's the definition of slope of any straight line graph? Rise over run. So the slope is equal to rise over run. Now, if you look at what is on each axis, the rise is position. So rise is change in the position. The run is measured in time, so the run is change in time. So the slope just is the speed. So I can look at this graph, and the steeper the slope, the faster the travel. And if it's a positive slope, it's traveling in the positive direction. If it's a negative slope, it's traveling in the negative direction. So I can look at this graph and I can tell all these things. Now, I did V average here. What if I want to find the speed at one specific instant, like right there? If I want to find the speed right there, what do? I do what?
Draw little lines.
Draw the lines. Well, what we do is we find the slope to, and this is a mathematical term, the tangent of the curve. The tangent of the curve just means the direction the line is at that point. So I draw a nice straight line that goes through that point, which in this case is the red line, and then find the slope of that tangent line. If it's a curving line, it becomes more complicated. You just find that tangent, draw the tangent, and then find the slope. Now, the second graph is showing velocity versus time. The velocity, like we said, positive for the first half, negative for the second half. The third one, speed versus time. Direction didn't matter there, so it's just the same all the way. So these graphs tell us a lot of things. In lab on Tuesday, this coming Tuesday, you're going to be walking and analyzing your motion in graphs. You're going to be working to learn to interpret these better. Yeah, what do you say? Okay, our next clicker question. A jogger runs from the south end of the Holmes Lake Dam which is close to where I live, to the north end, which is 1 mile. And it takes her 10 minutes. What's her average velocity? Nice. Converting from minutes into hours for you. Okay, give it about 5 more seconds again. Still coming in. Okay, we had 36 people that answered, and our answers were 2 said 6 miles an hour, 30 said 6 miles per hour north, 2 said 6 miles per hour south, 1 said 10 miles per hour, and 1 said 10 miles per hour north. No one said 10 miles per hour south. So when we look at these, once again, we have a clear majority, but we want to make sure everyone understands, right? Not just, oh, the majority understands, move on. So let's look at these. Why was the first one not correct? It didn't have a direction. It was the correct speed, but the question asked for the velocity, and the velocity needs the direction. So that's what was wrong with that one. This part C, remember, change in position is final minus initial. So ended up north, so it was going north by south. It was to the north. And so the south was the problem there. And the tens, how would you get 10 here for your calculation? Right, that would have been if it would have taken 6 minutes, which is 1/10 of an hour, then you would have gotten 10 miles per hour. Okay, back to kinematic equations. Kinematic equations is like the first real problems we're doing in physics. We do problems with these kinematic equations. You've already done a few, but we didn't really talk about them as kinematic equations. So the kinematic equations start from these three equations that are above the line, unless, of course, you're in calculus. If you're in the calculus class, then kinematic equations start with the definition of velocity and the definition of acceleration. You just integrate, as we did in class on Tuesday. So let's take this equation first. V average is delta x over delta t. Or expanding delta x and delta t, this would be so there I put subscript zeros because that matches the textbook. The subscript 0, just like a subscript I, means when you start at the outset. The 0 means at time equals 0. And I put finals, F for final. Now, if you look at the equations down below, they don't have finals. It's just saying x at time t. And so it doesn't need to put final on both. It's just understood that this is the position x at time t. So I'm going to go ahead and erase those finals. And now I'll take the equation I have written in red and solve it for position. So solve for position. Oh, one more thing. If we start our problem at time equals 0, then what is time sub 0 equal to? By definition, what I just said. 0. We do that so we can make that disappear and not have to worry about it. So now solving this for x, I first have to multiply both sides by the time t, and then I just move the x0 across. So doing it in steps, x is equal to, or x minus x0, forgot the x0 part. And then move the x0 across, and you have x equals x0 plus v average t, which is exactly this equation. So that's simply taking the definition of the average velocity and finding the position. So that's the first of our kinematic equations. I don't think it's super hard. Now for the second one, I'm going to take this equation and do the same work. So I'm going to have, for delta v, that's v minus v0. And it's t minus t0, but again, t0 is just 0. So doing exactly the same work as I did before, I will multiply both sides by t and then add v0 to both sides, and I end up with that equation. One caveat to using these kinematic equations. The top equation, v average, that works okay for me. The second equation, acceleration, that's only going to be true if the acceleration is constant. Right now, if I put a average then it still would have been true in any case as long as I calculate the average acceleration. If you are in physics 151, so that's everybody at Southwestern, half of the people here roughly, a little more than half, every problem we do is going to have constant acceleration. It might have constant acceleration here for 5 seconds, then constant acceleration at a different level for 5 seconds. But you're not going to have changing acceleration, just a continuous change. People in the calculus-based class, yeah, will have acceleration that changes with time. So it'll be a little more complicated with the calculus because you can do that. So these equations are for constant. Let me write this in black. Now, I realize the rest of those equations are probably not visible to the people over at Southwestern. When I made this slide, I just figured use the whole slide. So the next two equations, if you use the definition that V average, if you have constant acceleration, is going to be your starting speed plus your ending speed divided by 2. If you use that definition for constant acceleration, that's written right there. If you use that definition for average velocity, which is only, or average speed, it's only true if you are in a constant acceleration situation, then you can substitute into that V average, and it will produce this equation. Now, can you guys see that over Southern, or is that obliterated by the little boxes? Or Southwestern, not Southern. Southern. Can you guys see the equation, or do I need to write it? Okay, somebody gave me a thumbs up, so I'm assuming you can see the next equation. That is probably the most useful of the kinematic equations. You're going to use that like at least 80% of the problems you solve using kinematic equations. Now remember, you don't have to memorize these. They'll be given to you on the test, but you sure have to be able to use them. You have to know what they mean, what situations they're valid, and how to use them. Now, the final equation, which I am pretty certain the people in Southwestern can't see, so I am going to just write it in purple right here. X minus, that's not a minus sign, it turns out. That's our final equation. True story. When I was in college taking this class, my teacher didn't give us the equations, which is kind of rare, I think. And so on the first exam, we had a problem where I really needed to use this equation. I didn't remember it. And so I took the other equations and derived it from those equations, which of course took me like 10 minutes of work because I was a freshman. It's better to just have it given. You have a question?
You're working on deriving them, and you said that you're going to do them on the test?
I'm going to give you the equations on the test, yes. I will give you the 4 equations that are under the dashed line. Well, I'll also give you the ones above it too, but the 4 under the dashed lines are the ones that are really useful. So these 4 equations we call the kinematic equations. And we use them to describe how something moves, not why. The physics is really about the why. These are just equations to tell us how. And so we're going to learn to use these equations in problems. And I think right after this I have a how to solve problems. But one of the steps in solving the problems is identifying which equations are important for this problem, which ones you're going to use. And one of the easy ways to make that determination right now is looking at variables. So let's look at the equation that I wrote here in purple. It's missing one of our 4 kinematic variables. The 4 kinematic variables are position, speed, acceleration, and time. Which one is it missing? Time. So if you're doing a problem and the problem does not give you time and it does not ask you for time, look to that one because it's the only one that doesn't have time. Now, the second most important equation, or not the second most, the most important one, this one here, it has all 4 of the variables in it. That's the one you're going to use most of the time because it's the one that relates all 4 of those kinematic variables. If you have a problem that gives you like all but one and asks for the 4th or something in that range, you're going to have to use that one. If you look at the 2 above, This one here, the one in blue, it's missing position. If you have a problem and you're only looking at how the speed varies with time and you have the acceleration, or you have the speed and time and you want the acceleration, you don't care about position, then you choose that one. And then the upper one most, the average speed, usually we use that if it's constant speed. And so if it's constant speed, acceleration is 0, and we just use that. Of course, if it's constant speed, acceleration is 0, that's the same as the black equation, just putting in a 0 for A. So the top one, the one in red, really not very useful because the black one trumps it. Okay, one more thing on the slide before I go to how to solve problems. Notice the picture here. This picture shows a person dropping a ball, just like you did in lab this week. And when they drop that ball, it doesn't just stay in their hand, it starts falling, right? Everybody could have figured that out. And we talked about how Aristotle proposed that it was because of how much earth the ball had in it. But Aristotle also proposed, at least to the best of my reading, that it would fall at a constant speed proportional to the ratios of the earth and the water and the air and the fire. And so Aristotle, if you took this picture, this is just a stroboscopic picture. Well, it's not an actual picture. You can recognize that. Aristotle would have suggested that it should have gone the same distance each flash because it just falls at a constant speed. But an actual experiment, especially these days when we can make nice stroboscopic pictures, shows that clearly that's not the correct way. So you can instantly disprove Aristotle's theory, right? Our scientific model would say his hypothesis. So you can just do an experiment and disprove it. His prediction would be it should be constant distances each, fraction here, it's 1/10 of a second. So since Aristotle was wrong, we look at this and we say, okay, the distance is increasing between each 1/10 of a second. The first 1/10 of a second, it moved 0.049 meters. The second 1/10 of a second, you have 0.049 to 0.196. So that is a difference of, 0.14. Come on, help me out. I'm lame. 7? Is that right? Yeah, 0.147. So move 0.147 meters in the second 1/10 of a second. And you go forward and you see it moves more and more each 1/10 of a second. And so since you know those distances, since you have the position, you can find all the distances, then you can find what the average speed was in each gap. And so these here, actually I didn't calculate these, so I don't think they actually are the average speeds. I think those are the speeds at the end of each 1/10 of a second. But you can calculate the average speed during each one, and you see that the average speed was increasing. If the average speed is increasing, of course, that means the speed is increasing. I can drop the word average. If the speed's increasing, what is it doing? Accelerating, right? Because that's what acceleration is. It's a change in velocity. A change in speed is a change in velocity. So it's accelerating downward. And remember, our convention was that up is the positive direction. And so it's a negative acceleration because it's accelerating downward. And so once you have all this, you have the data, you can calculate what the acceleration is from how the velocity is changing. And what we find in experiments for small balls, not falling all that far, falling a couple meters, is that the acceleration is always the same, and we give that acceleration a symbol and a name. And so we say the acceleration due to gravity is equal to g, which is 9.80 meters per second, right? So what that means is each second, the speed increases by 9.8 meters per second. Now, I wrote this g as a positive number. If I write it as a vector, then it's either 9.80 meters per second squared down, or minus 9.80 meters per second squared up. So with the vector sign, it has direction, and it could be a negative if you consider up positive. Without the vector sign, it's just a magnitude. It doesn't have a sign. It's just the magnitude. Now, you probably noticed my units shifted here. I said meters per second the first time because it's changing 9.8 meters per second each second. The second time, I wrote that as meters per second squared. I wrote it both ways to illustrate the units. If you look at the first set here, these units, I thought I changed to red, those units seem to make sense. But if you look at the second set, really, it's still not red. Now it's red. That doesn't seem to make as much sense because what's a second squared? You can't square seconds. It's meaningless, right? But if you look at the units, a meter per second, using your whole, I've got division of fractions, you invert and multiply, and you'd have meters per second times 1 over second. And sure enough, that is meters per second squared if you just look at the units. So while second squared is meaningless, meters per second squared is a meaningful unit. Yes, mahalo. Is it mahalo or mahalo or mahala? Mahalo?
Yeah, Mahala with an A.
Mahala, okay.
So for the positive 9.8 meters per second squared, you have the direction going downwards. If it's
Well-
positive, it's supposed to go upward.
This one here is the scalar. It doesn't have a minus sign because it's just the magnitude. Then the one below, which is the one you're asking about, I understand. She asked about the sign of this one here. And because I put the direction is down, it's positive in the downward direction because its speed is increasing in the downward direction. So that's why it's positive in the downward direction, which is identical to negative in the upward direction.
So is this the only time that happens then in gravity? Otherwise, if it's one-dimensional, we say left, right, up, and down.
If it's one dimensional, you can say this is the positive direction of plus minus, or you can say left or right. Gravity is, by its definition, vertical. We define down as the direction of the acceleration of gravity. And so the acceleration of gravity is always down because that's the definition of down. Yeah. All right, here's our problem-solving techniques. Sadly, we're going to end on the problem-solving techniques. Instead of doing the problems, the next 2 slides were problems. So step 1, this is the textbook's list, is to examine the situation, determine which physical principles are involved. That's the real physics of the problem, by the way. Figuring out which principles are involved. And then you draw the simple sketch. On a typical test problem, it's 2 points for the sketch and 3 points for identifying those principles. That's half of your 10 points for a problem. Question, Katie.
I have a question about last slide. When we were throwing a ball straight up in the air, back down, on concept coach, it says acceleration is never 0 at that top. Can you explain that a little bit?
Okay. I can. I always like to answer student questions. You can read this in the textbook. I will stick with your question, but that's where I'm going to have to end. So the question was, when I take a ball, my test ball's in my office. Go ahead and change to a picture so they can actually see me, people, Southwestern. Okay, so when I take a ball and I throw it, during the time that I'm throwing it, I'm going to be accelerating it. Who knows what the acceleration is? So in these problems, we never talk about really what's going on until after it leaves my hand. After it leaves my hand is no longer touching it. It's no longer affecting it. We do have some forces at a distance. Gravity is a force at distance, but the gravity between my hand and this ball is so weak. It's what we call free fall. So it's going up there, and there's the force of gravity between the earth and the ball that's trying to pull it back down. And that force of gravity is causing acceleration. But that really doesn't answer your question clearly. So as it's going up, what direction is the velocity? As it's going up. Upward. Okay, so as it's going up, the velocity is upward. And what's happening to the speed as it goes up? It's slowing down. This would be better with the tennis ball because it's more visible, especially on the camera. Okay, so the speed is decreasing. that means the acceleration is in the opposite direction of the velocity. So as it's going up, the velocity's up, the acceleration's down. Now, when it's coming back down, what direction is the velocity when it's coming down? Downward. And is it speeding up or slowing down? Speeding up. So if it's speeding up, that means the acceleration is the same direction as the velocity. The acceleration is downward. Now that leaves us with the top. When it's at the very top, at the instant it's at the top, what is its speed? 0. Okay, so the speed is 0. 0 means it's not changing position, right? If the acceleration was 0, what would happen to the speed? It would stay constant. So if at the peak, when the velocity is 0, the acceleration was also 0, the ball would hover. I'd throw it up and it would just stay up there, never come back down. But it doesn't. It comes back down. So what direction did the velocity have to change to make it come down? Had to change downward. So it had a downward acceleration. And if we can ignore air resistance, throughout the entire flight, it had the same acceleration, 9.80 meters per second squared down. Now, I should have pointed out some textbooks say 9.81 meters per second squared. The acceleration of gravity does vary where you are, depending on where you are. Some textbooks use 9.81 because then it's really clear you have 3 significant digits. When you use 9.80, some people just write 9.8 and say, I only have 2 significant digits instead of 3. So that's why some use 9.81. Okay, we're out of time. Have a fantastic Sabbath.